Are you, are you hear
Yes,
me?
yes, yes. I hear you.
Okay. Dear colleagues, let us start our afternoon session. The first speaker is Professor Mojtaba Najafizadeh with the talk of shell supersymmetric continuous spin gauge theory. Are you ready, Mojtaba?
Yes, yes.
Okay, you have 30 minutes. Please start your talk.
Okay, okay. Thank you very much for inviting me and giving this opportunity to present the talk here. My talk is based on these two papers, which are supersymmetry, SUSY CSP theory. This is on-shell and this is off-shell formulation, which are based on these two bosonic and fermionic unconstrained formulation of CSP theory, and also based on these two papers by Metsaev, which are constrained formulation of CSP theory, bosonic and fermionic. Okay, this is my outline. Uh, Here, I will intend to find SUSY transformations for in the Schotter formulation and Metsaev formulation, and we will we will see how Metsaev formulation can be reduced to the to the well-known higher spin supermultiplets. Okay. Uh, Most of audience in this talk are familiar with higher spin and continuous spin. I just mention again that using the eigenvalues of Casimir operators of Poincare algebra, P square and W square, which W square is the square of Pauli-Lubinski pseudo vector, we can classify uh, massive and classify Poincare representation, which are massive and massless representations. In the massless case, we have two possibilities, which is a helicity representation uh, describing all higher spins particle, and another one is the continuous spin representation, which determined by this parameter mu. As you see, this continuous spin representation can be obtained from massive one by taking the limit, so as m goes to 0, s to infinity, while their product remain constant. And in addition, when we set mu equals 0, we will get helicity representation. That means that CSP theory at mu equals 0 should be reproduced an infinite tower of all higher spin results. We will see later. Okay, just to mention some words here, we know that lower spin and higher spin are referred to these particles, particles with a spin less or equal to 2, and higher spins are particles with a spin greater than 2, which are familiar with Franz-Stahl action and Fan-Franz-Stahl action. If we consider both of them, we can construct a bosonic CSP or fermionic CSP particle or field, which CSP stands for continuous spin particle, is infinite chain of all spin characterized by this continuous spin parameter. This is a naive picture that shows that all states are mixed by this parameter. When mu vanish, when mu vanishes, you will get an infinite tower of all spins, and also the continuous spin or the CSP is known by infinite spin particle or infinite spin gauge theory, which both called by Wigner in these years. Okay, in terms of these shapes that I showed you, one can refer to a scalar CSP or complex scalar CSP, which complex scalar CSP, by this we mean that it is a combination of two real scalar CSP. Also, we could have Majorana CSP or Dirac CSP, which again, Dirac CSP is a combination of these two Majorana CSP. We just note that as you know, in the massive Dirac equation of motion, it cannot be decomposed into two Weil equations because of this mass parameter, mass term. Similarly, for the Dirac CSP equation of motion, although it is massless, but due to existence of this dimensionful parameter, Dirac CSP cannot be divided into two Weil equations. Okay, first I showed you in terms of these pictures CSP supermultiplets in a nutshell. We know that in a SUSY theory, the number of degrees of freedom for the bosonic and fermionic part should be equal. But concerning the CSP, as I showed you, the number of bosonic and fermionic degrees of freedom is infinity. So a CSP supermultiplet denoted by this CSP and its super partner, which called it CSP no. These two fields, to construct a CSP supermultiplet, we have four possibilities. So as CSP can be real or complex, and also in the fermionic part, CSP can be Majorana or Dirac CSP, Dirac field. We found that among these four possibilities, only this case can be satisfied the SUSY algebra. So an unshell for the n equals 1 CSP supermultiplet is a combination of complex CSP and Dirac CSP. If you consider these pictures in the supermultiplet, we will see that when mu goes to 0, this CSP supermultiplet decomposes into the scalar or chiral supermultiplet plus all known integer spin supermultiplets and all well-known half-integer spin supermultiplets. I will show you more details later. As you see, for the scalar supermultiplet, we should take these two spin 0 fields, and we should take also this spin half from this tower, and the rest will divide into two integer and half-integer spin supermultiplets. Indeed, this shows that why we should have a complex CSP here and a Dirac CSP here, because to reproduce all supermultiplets. If we try to construct off-shell CSP supermultiplet, we should add an auxiliary complex CSP here, which is related to this picture. And again, at mu equals 0, you can reproduce all well-known supermultiplets, which are off-shell. Okay, let us go into Shossetero formulation. Shossetero formulation is an unconstrained Lagrangian formulation because there are no constraint on the gauge field and gauge parameters. Off-shell SUSY CSP action can be given by this action in this form, which operators B and F have this form. The S of phi action describes a complex CSP, which was found by Schuster and Toro first in this year. And however, in that work, the CSP was real. Here, because we need a complex CSP, we omit a prefactor 1/2 here from here. And in addition, this part is equal to Schuster-Toro action up to total derivatives. And the fermionic part, which is this, was obtained in collaboration with Xavier Beccart and Mohammad Reza Setare in this year. And in this work, we add this auxiliary action to construct off-shell SUSY CSP. Each part of the SUSY action has gauge symmetry. The bosonic part is invariant under these two gauge symmetry, and also the fermionic part is invariant under these two gauge symmetries. And this is the gauge symmetry for the auxiliary part. And equations of motion can be given by these relations. Now, we find that the off-shell SUSY CSP action that I showed you is invariant under these supersymmetry transformations, which operators L and R are chiral projectors, and the operator X should be in this form. So the off-shell SUSY CSP action in the Schuster-Toro formulation is invariant under these transformations. Here we note that both chiralities in the Dirac field are participating in the SUSY transformations. If we rewrite this variation of phi, we will see that if we rewrite this term, we will see that both chiralities are appeared. We check that the commutator of supersymmetry transformations are closed off-shell up to 2 gauge transformation parameters, which these two gauge transformation parameters are in this form. I showed you already these transformations for the fermionic part, but here the gauge parameter is field dependent. It's dependent on the field phi. If we apply the equation of motion, this will disappear, and we will get unshared result that we obtained already. So the algebra is closed off-shell up to 2 fermionic gauge transformation. Let us go into constraint formulation, which is Metz formulation. In this formulation, gauge fields and gauge parameters are constrained. As you know, they are double traceless and so on. For this case, the off-shell SUSY CSP action should be in this form, which operators B, B mu, B0, F, and F mu are given in the next page. They have long terms. And the first term, this is a typo, this is S of phi. The first term describes a complex CSP, which Metz found in this year. At mu equals 0, this action is exactly the Franz-Stahl action. And also, the fermionic part describes a Dirac CSP, and again, at mu equals 0, this term will vanish, and this would be exactly Franz-Stahl action. And this auxiliary field is the one that we add here to construct off-shell SUSY. These operators are given in this form. As you see, the B operator is proportional to the Franz-Stahl operator, and here the F operator is proportional to the Franz-Stahl operator. We should just extract a prefactor to see that this relationship. And omega bar, I mean the derivative with respect to omega, and n is this. Similar to the previous case, each part of the off-shell SUSY action is invariant under these gauge transformations, the bosonic part and the fermionic part. We will see later that the off-shell SUSY SUSY algebra should be closed up to this gauge transformation, which in which the gauge parameter is field dependent. And as I said, gauge fields and gauge parameters are constrained. The gauge fields, bosonic fields are double traceless, traceless, gamma traceless, and triplet gamma traceless. Equations of motions would be in this form. Then we find that considering the off-shell SUSY CSP action in Metz formulation, it would be invariant under these supersymmetry transformations, which operators T, Y, Y mu, X, X mu, and Z are in this form. Okay. Now we would like to reproduce higher spin supermultiplets using these transformations and these operators. And as I said, the commutator of SUSY transformations on the fields will close off-shell up to gauge transformation parameter, which is field dependent. Okay. To reproduce higher spin supermultiplets, we first take into account the gauge fields in terms of real fields. Our fields were complex, but if we rewrite them in terms of these real fields, and if we extract the first term of phi, phi prime, h, h prime, and psi, and except psi prime, because psi prime will participate in the half-integer spin supermultiplet, we just extract the first term of these fields to construct the West-Domino model. Similarly, we can have such a relations for these fields. Then, using these considerations and setting mu equals 0, we will see that the off-shell SUSY CSP action in the Metz formulation reproduce to this, in which these actions are given, which this action is exactly West-Domino action, off-shell West-Domino action, and this is the action of integer spin supermultiplet, and this is the action of half-integer spin supermultiplet. Okay, now we want to extract the supersymmetry transformations from the CSP transformation. For this purpose, we consider these operators, T, X, Y, Z. We note that at mu equals 0, Y mu and X mu will vanish, and we will remain with these four operators. We divide them into two parts. Each operators will divide into parts, in which the operators with index 1 will appear in the integer spin supermultiplet, and the operators with index 2 will appear in the half-integer spin supermultiplet. Okay, for the scalar, for example, for the scalar or chiral supermultiplet, we should consider these operators in this form, as I show you again these transformations. If these transformations act on the scalar fields, these are derivative with respect to omega, so this will vanish, also this will vanish, and this. We will remain with 1, ds slash, minus ds slash, and 1. These are operators that appear in the chiral supermultiplet, as I showed you here. By this consideration, the offshell action of the scalar supermultiplet would be invariant under these transformations, the transformations. We note that we arrived to this result from a top-down approach. Indeed, we didn't check that whether these are this action is whether invariant under this. We just obtained this result by from the CSP gauge theory. And similarly, we can reproduce integer spin supermultiplet results. As I said, we should consider the operators t, x, y, and z with index 1. Then we will see that off-shell action of the integer spin supermultiplet that was in this form would be invariant under these transformations. If we consider unshell transformations, that means that we should apply the equation of motion. Applying the equation of motion, these and these two terms will vanish, and we will remain by variation of phi and psi up to here. Such unshell transformations are exactly results by Cartwright that found in this year. Finally, for the half-integer spin supermultiplet, we should consider that operators with index 2, as I said, and then we will see that off-shell action of the half-integer spin supermultiplet, which was in this form, would be invariant under these off-shell SUSY transformations. Again, applying the equation of motion, these terms will disappear, and we will remain with these transformations, which are exactly transformations obtained by Cartwright. To conclude, I just recall again this picture that I showed you, that CSP supermultiplet should be contained in two complex bosonic fields and a Dirac field, which in the at the higher spin limit, I mean mu goes to 0, we reproduce all supermultiplets. Thank you for your attention. Sorry, I can hear you. Yeah.
Again, the questions from Fedoruk. Is possible to represent the model which you present in superspace formulation, and which superfield will be used in such superspace formulation?
Good question. It's an open question. Indeed, we didn't try to find these transformations in superspace. It would be a good question because if one construct off-shell, indeed, CSP transformations in superspace, then at mu equals 0, it should be reproduced superspace results by Kuzenko. I didn't try it.
Thank you. One more question, please.
Hello, do you hear
Hello.
me?
Yes, yes.
It's
I
just
do.
a book builder.
Yes, yes.
Could
I
you
know.
please comment the point where the algebra of supersymmetry transformation is not closed in your case? In your case, the commutator of transformation is in the right hand side contains some strange for me terms. Okay, understand?
Yes, it's close up to gauge transformations.
But in principle, superalgebra is completely defined without relation to concrete fields. So does it mean that you can make some gauge transformation, obtain the standard commutation relations?
You mean the commutator should be closed without
Yes, I believe it should be.
uh,
Or maybe
at
it's
least.
possible to make some gauge transformation and transform to standard form.
I
Hey,
see.
maybe you think.
But you know, in the on-shell formulation, the work of Cartwright is similar to this. In the Cartwright work, he closes the algebra up to gauge transformations. And but in the off-shell case, this is a good question that we should try that whether we can find another transformations to kill the gauge transformation in the algebra.
If there are no questions, Omok, you? Thank you. Speak again.
You're welcome.
Thank you very much.
Thank you. You're welcome.
See you later.